Um, so welcome everyone to this introductory session to Introduction to R. Andre already talked a bit about R. I hope you all had downloaded it and installed it. I'll be using RStudio as the interface for R. That's what you see now on my screen. I have opened all the scripts that were put available for you on the cloud. So I will just go through the script and commenting as I go. It's not meant to be really interactive. If you have any questions, please post them in the chat and we'll try to address it. We don't have so much time, so it might be a bit condensed. But in this script, you will also find links to other resources, which I highly recommend looking into. There are a lot of introductory courses on R out there on the web, which like some of them are of really, really good quality. So if you can't follow everything in this session, maybe have a look afterwards. This introduction is meant really to give you like the basic knowledge of R. It's not exhaustive. There are many more things that you will probably use and need in everyday life, but I think it's a good starting point so you get familiar with R and how it looks, how it feels, and its capabilities. And without further ado, let's jump into it. So as I said, I put some resources here for you so you can look them up afterwards. Some instructions how to install R. Hopefully you've done it already. Repositories of R packages. So these are libraries of functions that we use in R. And let's jump straight into it. As I said, I will run my code in the script, so you'll see hopefully as I go what I'm doing, and I'll try to comment what I'm doing. First, maybe just let's have a look at the interface. In the top left corner, we have our script. This is the code that we save. So we write code here to run it afterwards. On the bottom, we have the console. We can also write code here, but this code will not be saved. So, and all the output of the code from the script will also be outputted in the console, so on the bottom left. On the right, we have multiple panels. We have files, so we can open scripts. From here, we have plots, packages where we can install, update, and unload packages. And we have, very importantly, help, which we'll use extensively. And then on the upper part, we have the environment. So here, all the variables we define will show up. For now, it should be empty because we didn't use anything, and we won't need it for some time because the most basic use of R is basically like a calculator. So we can have just basic arithmetic operations like summation, subtraction, multiplication, division, squaring, and like in two different ways, or like simple math functions like logarithm. How I run this code from, I have to tell this before we go on. I run this code just by going to a line in the code and pressing Control Enter, and that runs the current line from the script. I can also select multiple lines and then also press Control Enter, and it will run all of these lines. Another way, if we want to, like if we have a whole script and we just want to run it, we can also go to source, and this will run the whole file, so the whole script from beginning to the end. This is important to know, like R always reads the script files from top to bottom. And unlike in Python, for example, where you can define a function anywhere in the file, here the function has to be defined before actually using it. Okay. But before functions, we have to look at variables. So to define a variable in R, we use this arrow symbol. So, and this way we define x, the variable x, which is number 5. We can also use the equal sign, but normally we use this only inside functions. We can also use it the other way around, so from left to right, but that's less common. And the name of variables is arbitrary. It only must not start with a number, so it must start with a character. Okay, so we've defined now 3 variables, x, y, and z, and we can do arithmetic operations on them as well. So if we want to sum x and y, or like more complicated operations, as you can see there, I get the output here on the bottom in the console. In R, variables have different classes. So these are different types of variables. So our x variable is a numeric because it's a number 5. And the type is double. So a numeric has 2 types. It's either integer, which is, or double, which has decimal places. We can also make, we can also ask if it's an integer. 5 is, so we've seen that it's a double, so it's not an integer. So that's why we get false. But we can convert it to integer with a function as integer. And then the class of xx is integer. So I've called some functions here. Functions are in my code shown in red, and always take arguments in round brackets or parentheses. Then the second class of data is of variables are logicals. So these are values of true and false, which could be written as true. So with the whole word true or false, it could be also abbreviated with T or F, or even encoded in numbers as 0 and 1. So, and we can have different logical operations. So for example, if we have a variable x that is 3 and y that is 2, we can ask, is x smaller than y, which is false? Is it smaller or equal than y? It's also false. Is x bigger than bigger than y? That's true. Is it equal? It's false. Is it different? that's true. And then we have this exclamation mark, which this is a symbol that inverts the logical value. So x is, here we have x is x smaller than y, which is false. But if we run the whole line, it gives true because this exclamation mark inverts the false into true. And we can also save logical into a variable, and it's of class logical. Then we have and or operations. So if we have z that is true and h that is false, and z and h gives us false, because both have to be true for this expression to be true. Or on the other hand, so we have true or false, and if either of them is true, this will give true. And we can convert true and false into numerics, so to ones and to zeros, which is very neat because it simplifies a lot of things. Okay, the third class are the characters. So basically, these are text words. For example, our variable animal has a value of dog, and this is, and we cannot use algebraic operations on it, so it will give an error if you try to multiply it by 3. We can also sometimes have numbers encoded as characters. This often happens when we're reading data from outside, so from a table, and sometimes the data will be read in as character, but we can, R is smart, and it can convert this kind of characters into numbers just by calling as numeric. Okay, then we've seen R gives out values, errors if it doesn't like something. For example, a different kind of error is division by 0, which gives out inf, so infinite. And we can ask it if this is NA, which is a not unknown number or unknown, and it gives false. We can compound characters or combine characters with a paste function, where we just concatenate multiple characters into one. We can combine just directly words with variables, and this, for example, would give us this whole expression as just one character. For example, paste by default uses space as the separator, but we can also define different separators, for example, this minus sign here, and we can, for example, make a date format out of this. Okay, so when we have our data types, we can condense them, or we store them in different data structures. The simplest structure is a vector. And we construct a vector using this function c. And then in parentheses, we just put in the values we want. So for example, this creates a vector of values from 1 to 5. And we can save it to a variable x. And the class is still numeric because all the values in the vector are numeric. Simple way to construct a vector of like a sequence is just by writing, for example, for a sequence from 1 to 10, just one column 10. And this will give us a sequence from 1 to 10. We can also do it with seq function, where we can define a different step, for example, by 0.5. Vectors have a length, so length of x, so this was the sequence from 1 to 10, is 10. So this is just one dimension, and its length. We extract the values using these square brackets. So for example, we can extract the third value, which is 3 in this example. We can extract fourth to sixth element, or we can specify a vector of indices that we want to extract. Here to notice, for those who are maybe familiar with Python, Python has indexes from 0 to n-1, and R has indices from starting from 1. So if we have a vector that has a length of 10, first value in the vector has index 1, and the last has the index of 10. Okay, so we can also have logical operations on vectors. For example, which elements of vector x are bigger than 4, and it gives us again a vector as an output with logical values. And this is useful when we want to subset the vectors. For example, here we can subset vector x, where we choose only those elements that are bigger than 4. Vectors can also be named. So for example, if we have vector from 1 to 5, we can assign names by function names, very convenient. And we can also subset this in the vector by name. So we can extract the element that has a name of AA, which is 1, or AA and CC, which is 1 and 3. And you see in the output, now the above elements, we have names. Then we come to operations with vectors. We can multiply the whole vector just by multiplying with a number, or we can square the whole thing. We can sum two vectors, multiply two vectors together, or like even put to power over a second vector. And here it's to notice like y has the length of 5 because it's from 5, it's a sequence from 5 to 1, and x is a sequence from 1 to 10, and it still works even though there are different lengths because R automatically recycles. So in this case, it used y vector 2 times. Okay, if we want to add vectors together, we just use again the C function to compound them together. If we want to remove the elements, for example, if we want to remove the first element, we use -1, or if we would want to remove the second, we would use -2, like this. And we can also do the more specific subsets by names and so on. Okay, so I've used multiple functions by now, and often we want to know, we don't know exactly what the arguments of the functions are or what the functions do. That's why R has very handy help files. we can access these help files by writing question mark and then the name of the function. And if we run this, it opens the help in the right bottom side. We can do the same with help and then as argument the name of the function. Or we can navigate with our cursor on the function and press the button on the keyboard F1. That works as well, for example, for which. And here in the help file, you have a short description, usage, where all the you see all the arguments and their default values. And then all the arguments are listed with the description. Value tells us what the output of the function is. And then we have nodes like additional resources or related functions and important examples as well. So, yeah. Now the second, a bit more complicated structure is a matrix. So a matrix has two dimensions. It has columns and rows. For example, we can create a matrix of ones with 3 columns and 2 rows in this way. So we specify first the input data and then the number of columns and number of rows. We can also convert a vector to a matrix like this, for example. So we have a vector from 1 to 6, and we convert it to a matrix that has 3 columns and 2 rows. And there are 2 ways of doing that. We can do it by column. So we start in first column and fill it first, and then the second, and then the third. Or we can do it by row, by filling first the first row and then the second row and so on. And then in this case, we have to add this by row is true argument. Okay. So, and the class then is matrix array. The dimensions, so we can ask what are the dimensions of this matrix, and it tells us 2 and 3. So first dimension are the rows, and second dimension are columns. We can also ask about the length. In this case, it's 6. So this is the number of all elements in the matrix. Or we can ask specifically how many columns there are or how many rows there are. Okay, so extracting values from a matrix. Here we also use the square brackets, but now we have to specify 2 dimensions. So if we want to select one element, for example, second row and third column, we do it like this. But maybe we want to have second row and second and third column. We would do it like this. And if we want an entire row, for example, we leave the second argument here empty, and this means take all. So this will give the whole second row. And we can also specify if things are not in order. For example, first and third column, we have to use vectors in the subsetting. Okay. Then before vectors only had one names, but matrix have 2 dimensions, so we have 2 names. So for columns and for rows. And we can define this by col names and row names. And we can again subset the matrix by names. We can, of course, do mathematical operations with matrices. We can add 3, for example, multiply it by 3. And if we have a second matrix, we can add them together, which is done by each element. So elements in the same place will be added together. We can also combine the two matrices by adding additional columns with cbind or adding additional rows by row bind. Okay. And we can also do like linear algebra, like matrix vector multiplication, for example. Okay. Probably the most used data structure is a data frame. Data frame is different from, it also has 2 dimensions like matrices, but it's different in the way that each column can have a different data type. So matrix can either be like a numeric matrix or a character matrix, but you cannot mix. In data frame, you can mix. So let's just create some vectors, and we can add them together into a data frame with a data.frame function. And data frame always has column names. In this case, the column names were created from vector names, as you can see here and here. But we can override this by specifying the names we want. So we can just, for example, for the first ID column, we want the name code, like this. Okay. We can also have like just one column from a single vector, like this. So as I said, names, they're column names, and we can extract like just one column name, for example. We can also change just one column name. For example, if we say names and then we subset this just to 1, we can change it to ID, for example. And this will change now, as you can see here, the first column name was code, and then we change it, and now it's ID. Okay. Then extracting values from data frame is very similar to matrices. So we have again 2 indices. We can extract again by column names, for example. That's very common. What we can also do is subset with this $sign operator. So we have a name of data frame, then $sign, and then the name of the column. What RStudio does is very handy. For example, if we have a data frame name, and then we write data frame, it will automatically suggest us names or column names. Okay, and then yeah, we can mix and match. Like we can say, okay, take the rows where the in AR column is more than 700, and keep just the column stat names. So there's a question. Main difference between data frame and matrix is that in a matrix you can have only numeric values and or character values. So one type. In data frame you can have each column with a different type. So you can have maybe like we have here. The first column ID, it's a numeric, and then the second column, it has character values. Again, third column, again, character values, and the fourth column numeric values. And you can combine these in arbitrary fashion. It doesn't matter. Okay. Sometimes we're not sure what the structure of our data frame is, and that's when str function comes handy. So this tells us that we have a data frame with 3 observations and 4 variables. So observations are a number of rows and variables are number of columns. And then we have each column, and then it tells us what kind of type of data there is, and the actual values. Okay. And if we look for our matrix has a bit different like output for structure. And then we come to last data structures we will cover, and these are lists. Lists are like the bedrock of data structures. They really like they're the most simple, the most basic data structure. They can include anything. So we can have in a list, we can have a combination of vectors, matrices, data frames. It doesn't matter. List will take everything. It just lists different things. And if we look at the structure of this list now, the first element is a numeric vector. Second is a matrix of integers with these dimensions. And then the third element is a data frame with these parameters. So so if we want to extract things from a list, we now have to use double square brackets like here. So if we want to extract the data frame out of this list, we have to use double brackets and 3 for the third element. We can also name the list, so to make it more convenient to extract. So again, we can extract by name as well, or again with this $sign operator. Yeah. We can also add things to a list just by saying, okay, the fourth element of this list will be another matrix, and the fifth element is a vector. And then we have, what did I do? Sorry about that. Yeah, if we just want to see, now we have a list with 5 elements. I guess you can't see my screen anymore. Sorry about that. Just a second. Okay. Then just someone. Okay. Yeah. Thanks for letting me know. Okay. Moving on. Now we know the structures we use in R. Now we go to functions. So function is also basically a data type, and we define a function simply by assigning a function to a variable name. So here we'll write my first function, and we do this by calling function, and then we have three arguments x, y, and z, and then in curly brackets we have the body of the function. And here we have some mathematical operations, and then we return an output. So we will, the output we will give from this function is this variable output. So if we do that, we'll see in the environments here under functions, there is now my function. And then we can use this function again, like my first function with arguments 1, 2, and 3. It gives 1, or with these arguments it gives 5, or we can assign values to arguments by name, and then the order is arbitrary. So if we just omit the names of the arguments, then R presumes the order that's given here. So if we just use 1, 2, and 3, X will be 1, Y will be 2, and Z will be 3. But we have to specify, if we have different order, we have to specify the name. Okay. So yeah, we can also have a function that simply prints a world, for example. But mostly, I mean, a lot of times we don't write our own functions, but we get functions from packages. For example, we can install packages just with this function install packages, and then the name of the package, and then there are some additional arguments. I will not do that now because it will take some time, and I have it installed already. But we can load the library and all the functions and data that is inside this package by calling library. So if I do that, you see loading required, and then it loads this package into the environment. This is just a data package, so we don't see anything, but we'll use this again later. Require is similar to library, but it's mostly used inside other functions. So it tells that some library is required to run the function. Okay, then next thing is flow control. So those that have used different programming languages will be familiar with that. First thing is if statement. So if statement is basically it changes how the script works. So with different conditions. So if we have A, it's 512, and we ask if, so this is our condition, if variable A is an A, so if it's unknown, then it will print this. If this is not true, it will move to the next condition. So it will move to else if. And again, we have a condition if A is more than 0. If that is true, it will return a square root. And even if even that is not true, then it will go to else, and else doesn't have a condition. So this is like a last, if all previous conditions were not met, then do this. So, and if we run this all together, it gives us out a number because, and this is a square root of 512, because the condition of A is bigger than 0 is true. Next, we have a for loop. So loop is a thing in programming where we basically iterate and loop over the same code over and over again. And in this case, we will iterate over I, where I will have values from 1 to 3. So in first iteration, I will be 1, and this here it will get a character. The square root of 1 is 1 times 1. And then it will print this text. In the second iteration, I will be 2, and here we'll have 2 and 2 times 2. And 3, again, the same. Let's see the output. So this is it. And we can also iterate over characters, for example. It doesn't matter. So now our iteration variable is j, and it will print all these names one after the other. Okay. Then we have a while loop. While loop is a bit different. It doesn't have a fixed iterations, but it will iterate as long as the condition is met. So for example, if we have j is 10, and then while loop will check, is j more than 0? If so, if true, it will print j and subtract 1 from j. And then it will loop around and it will look again. Okay, is j still more than 0? If so, print and subtract 1. And it will continue to do so until j will be less or equal than 0, and then it will stop. So let's see what this does. So it prints numbers from 10 to 1, and it stopped, like when it printed 1, it then subtracted 1, and then j was 0, and when it checked again, is j more than 0? It says no, it's not, and then it stopped. Okay, we can also stop the loop with a break. So maybe if some condition is met, we want to exit the loop, and then we use this break command. Also, if we want to skip one iteration, or skip to the next iteration, we use next. For example, here, this will skip when I is 1, 3, 5, or 7, and it will break after when I is more than 8, and this is the output we get. Okay, the next thing is very similar to loops, but just in a more compact form are the apply family of functions. So if we have a matrix like this, and we want to get sums over each row, we can use apply, and then first argument is the data, then is the either rows or columns. So 1 is rows and 2 is columns, and then a function that we want to apply on this. And this will give us the sums of rows. And similarly, we can do sums, means of columns. Then we have a lapply and supply. So these are more general apply functions. So if we iterate over names and we want to know how many characters are in each of these names, we can use the lapply, and it will give us a list for each of these names with the number of characters in it. And then if we do the same thing with supply, supply will unlist the list into a vector, which is the same as if we would use unlist function here. Okay. The last thing in this part is reading and writing of data, which comes like really often in our workflow. So I have prepared some data for you that we want to read. And like here, I use read table function to read this CSV file. So so first argument is a file name. So here I use a full file name to a folder in my computer. You will have to change this to reflect your own directory when you have the file. And I can do it like this, and we get a data frame. The second option is what I often use is to define a directory where that I use. So like this is a name of the directory that I save into a variable, and then I paste the directory name and then the name of the file to get the full path or full file path. Otherwise, each R session has its own working directory. So for example, currently my working directory is this file path, but I can change this directory into the folder where I have the files for this workshop. And then when I read in the files, I can omit the whole directory part and just use the file name. It works just as well. So we have now a huge file here, a huge data frame, and sometimes we cannot output it in the console. It just looks small and we don't see everything. And we can use the view command to view this whole data set in a separate window like this. Okay. Yeah, and useful commands are also head and tail, which will show just first. Head will show first 10 elements or rows, and tail the last 10. We can also have like a summary. So this is useful. This will tell us for each column in a data frame, like for example, minimum and quantiles and median. It depends what kind of columns you have, what kind of data. This can vary. Or structure, we've looked into that. Okay, so maybe if we use this data now and we want it to, this data is precipitation data in rainfall gauges in millimeters per month, but maybe we want to have it in meters per month instead. So we want to divide it by 1,000 and then write it to a new file, which, for example, we do it with write CSV. First, we have the data, and then we have the file name. We can also save into a different format. For example, in RDS, this is a R-specific format. It's very fast. It saves variables exactly as they are, so with everything preserved. And it's also very memory efficient. So big data frames will be much smaller in this format than if exported to CSV or Excel or something. And we can read those files back with read RDS. Then often we have to read data also from Excel. I use for this here a package called read Excel. And the function inside this package, which is called read Excel again. And we read this Excel file for sheet and then the range where the data is. Can look at the data. Okay, that was the first part. And as I don't have too much data, we'll just really briefly go through data wrangling as well, because Andre will use some of the principles from data wrangling in his own part later on. So data wrangling is basically taking raw data and converting it to a meaningful data that we can use for further use or analytics. And it has three principles. The first is that every different variable in our data set should have its own column. Every observation, so for example, if we measure length and width of a plank, length and width will have its own column. Different observation gets its own row. So each plank that we measure will have its own row, and each measurement that we make will get its own cell. And a very good package collection for data wrangling in R is tidyverse. Tidyverse has a lot of ease of use, like helpful functions that really make it easier to wrangle the data around, and we'll look at some of them. So first, I'll load this and set the directory again, load the data again. And tidyverse uses tables. Tables are very similar to data frames. They more or less behave like the same as data frames, and for now we'll leave it at that. The second thing we have to talk about in tidyverse are pipes. So instead of nesting different functions like this, so if we have like a data frame A, and we want to first do a function G and then a function F, we can do this by with pipes in like this. So we have A and then a pipe, which is this operator here, and then function G, and then function F. Why use this? Because more or less because it makes the code much more readable. So it's, and in some instances also faster. And we don't want to make one operation, for example, and then save it, and then on the same variable do another operation and save it again, because that's also computationally intensive and memory intensive. So let's just look at a simple example. If we have a sequence and we want to make a sum, we could just write sum and then a sequence, for example, and get a sum. But we can use this with pipes, and we have data, then pipe, and this data gets piped into this function, and we don't, as a first argument, so we don't have to specify the first argument. If we want to put the data in a different place as the first argument, we use a dot. So this dot would represent the data that is being piped. But you will have to read this. It's here, everything is explained, but we don't have so much time, so I'll just go faster. There are other pipes as well, but this is also a bit more advanced. And let's just go over some functions that are in tidyverse. So if we want to select specific columns, we use the select function. If we want to select specific rows, we use the filter function. If we want to add or change columns, we use the mutate. So for example, this example, we have this precipitation data. The first column is a date. Other columns are different precipitation gauges. And we select first 3 columns. And then on those, and we then add a new column with this name, which is a column with this name divided by 1,000. And so we selected first these 3 columns, and then we created 2 more. Similar function is transmute, but the difference is that transmute adds new variables, but drops all the existing ones. So, for example, here we created one new variable, but all the others were dropped. We can also change an existing one. So, for example, we can just change date, which already exists, and we change the format into date format. Okay. Yeah, so the format of the date change. Then a very important feature is grouping. So we can group the values or rows by specific values. For example, we can say, okay, we want to group the rows by year. So with the help of this function from lubridate package, we calculate the year from the dates, and we group the data by years. And when you output this table, it would say groups, and we have 10 groups by years. And this is useful when we are summarizing. Summarize function will decrease the number of rows. So we calculate some kind of a statistics. Either for example, here we can calculate the mean, the minimum, the maximum, and the mean. And we just get one value, even though we have a lot of values otherwise per month. Then there are other functions that I will not get into. A very important thing is also pivoting. So pivoting is changing the data from long format to wide format or vice versa. For example, we have here a data in a wide format. So we have date and then just a lot of precipitation gauges, which does not fit with the principles of tidy data frames. So we want date column and then name of the gauge column and then actual measurements, so the precipitation. And we can do this with this pivot longer functions where we say, okay, we want to pivot into longer format all the all the columns that start with P, so all the rain gauge, and we'll save these names into column with name gauge, and the values will go into column with the name P. And that's a new data frame that we get in a long format. And we can convert this back, but I'll not get into that. And then I'm not sure if Andre will cover that, but we often want to join the columns, and we do this with joins. So basically, we join data from, or add data from one data set to another. But I'm running a bit out of time, and I don't want to take time from my colleagues, and this is maybe more advanced topic. And you have some resources written here at the beginning where you can learn more about this. And maybe, yeah, as I said, it's a more advanced topic. And I would rather, maybe if we have time at the end, return to that. Otherwise, I would leave the floor to Claudia.
So hello from my side. As Lauren said, I'm Claudia, and I will present a visualization with R, let's say. So we will learn how to create basic plots or graphs that are most frequently used also in the field of hydrology. So I will share my code. You should get this code yesterday. So you can follow me by running this code. I would like to say at the beginning, I would like to introduce myself first. So I am a PhD student at the University of Ljubljana, and I'm using R for my research. So I'm an average user of R. And I prepared this code together with a colleague from Czech Republic, namely Vojta Svoboda, who works as a hydrologist at the Surface Water Department of Czech Hydrometeorological Institute in Prague. And he's also using R for daily work, mostly for statistical analysis and visualization of data. So none of us is, let's say, expert in developing R. We are just users of R. However, we hope that this visualization part will be understandable to you, so you will learn how to use R to create some nice plots for example, for your papers or for your for communication of your research in the future. So first of all, you will need to set your working directory. So it means that you need to copy the path from your computer where you have stored the data that were prepared for this part of the workshop. And for this part of the workshop, so for visualization part, we will need some packages. I hope you already installed them. We will need ggplot2 package, which is dedicated to visualization of plots. Then we will need a data table, which enables us to do with tabular data and enables, let's say, faster calculations when we are dealing with large data sets. And we will use the library Zoo, which will help us just to convert our data to the time series. So we run these lines. I prepared two data sets for this part of workshop, namely the climate data from two locations in Slovenia. We downloaded the data from the Slovenian Environment Agency website, and those data are freely available. We downloaded the data for the Ljubljana station and for the Rateče station. Ljubljana has more continental climate, while Rateče is located in the mountainous area. So we could expect some differences between the two locations. So we will first read the data sets, and then we will look into the data a bit. So we read the data table, which is stored in the txt format by using the function read.table, and we will save it into the variable cl1. Then we will use the function as.data.table. So this is a function from the package data table that was mentioned before. So we will use it for faster calculation in the next steps. And then we will add additional column to the data set, which will be named station. And in each row, there will be written Ljubljana. All the explanations are added to the lines. So if you are not able to follow me right now, you can go through the code alone later. And now we will look how the data look like. By using the function head, we can see first 6 rows of our data. And we can see that in our data set, there are five columns. I didn't run this line probably. Yes, so we have now 6 columns. This additional station column was added to the data set. So we have year-month column, meaning the year and month of the data. We have data about the air temperature, namely mean average temperature for each month from year 1991 to 2020. Then we took also the average relative humidity, the average sun duration in hours, and the monthly sums of precipitation. And we will do the same for the second data set from Ratece station. So we will read the table, we will convert it to the table, and then we will add a column named station. And here in each row, the value Ratece will be added. And we can also look in this data. We see that the structure of 2 data sets is quite similar. And here in the last column, you can see that this additional column was added. And now what we will do, we will join those 2 data sets into a new variable CL, which we will do by using the function rbind, which was introduced by Lawrence before. So what we will do, we will join 2 tables. In practice, one table will be below another. So first we will have a table of Ljubljana station, and then below it, it will be the table of Ratece station. And now we will use so-called zoo package, which I said we will just use to convert our data set from indexed data set to time series, because this year month R doesn't know that this is actually a date. So we have to say to R that our data set is actually a time series. We will do it by adding additional column to this CL table. As we will see when we execute the code and look into the data, that additional column was added by name date, and month and year is written for each row. So this form was taken from the computer. So let's go to the fun thing. I said that we will be doing on visualization. So first of all, I will introduce you some three basic plots without using any packages. So we will use function plot, which is already in R. So you don't need to install any additional package. First of all, we will create a scatter plot or point plot. Then we will create a line plot, and then we will create histogram. So creating graph by using plot function requires for you to say or define some arguments of the function. For example, which data we want to plot. So on our x-axis will be plotted sun duration taken from the CL1 data table, which was Ljubljana. And then on the y-axis, we will plot temperature of this station. And we also defined the name of the axis, both y and x. And we can also say which color we want our points to be, because we didn't define that we want a point type of a plot. By default, the plot function is set to point chart. So we said that our color will be forest green. You can find colors that are available in R and how to call them on the internet. You can just use basic colors like green, blue, red, and so on. Then we can also define type of the point. So if we want, I don't know, rounded dots or perpendicular dots or something else, but types are numbered, and you can go on this link, which I pasted in the script, and you can see to which shape of the point each number corresponds. So I will just run this plot now, and we can see that we got quite nice plot where on the y-axis are average monthly temperatures in Ljubljana, and on the x-axis sun duration in hours. Similarly, we will plot line plot, but by using temperature data from Ljubljana. But here we have to define that our plot will be line. We didn't do the same with point plot because it's default. And we will also say what will be the name of the y-axis and the x-axis and which color we want to use. So we decided for the red color. And here is our line graph. We can see that we didn't define our x data. We just said what should be on the y-axis. So our x-axis is actually index of the month. The third plot is histogram. We will plot here precipitation data from the Ljubljana station, and we define histogram by using H letter. And on y-axis, the name will be monthly precipitation. There is some typo in the name. And on the x-axis, there will be name index of the month as in the previous plot. And the color will be blue. So this is our histogram of precipitation. So you can use basic function plots to create some nice plots, but we decided to present you a package ggplot2, which is dedicated to visualization. Let's say it gives you more options. We will also in this scope with ggplot2 create a line plot, a histogram, and point plot, but on the different data. How we are creating plots by using ggplot2 package, we have to start always with ggplot and then brackets, where we say which data we will use. And then we are adding layers, and we are adding layers by using plus operator. For example, here in this line, you can see that this geom line is another layer for ggplot. So with ggplot2, we can also select different colors, different types of points if we are plotting point plot, different different transparency of the points or lines, and so on. There is a lot of literature in the internet and a lot of examples how to use ggplot to create different types of plot. So if something is not covered here today, I advise you to go on the internet, and I'm sure you will find everything what you will be looking for. So first, we will plot the line plot, and we will use the air temperature in Ljubljana for the whole period. So from 1991 to 2020. So we start with the function ggplot2, and we say that our data will be CL, so the joint the data table, but we call data for the Ljubljana station by defining that station should be Ljubljana. This is the additional column that was added to the data set later. And in the plot function, we defined a line plot by using a type is L. Here in the ggplot2, we defined that we want line plot by adding a layer geom line. And then we also say which parts of data table should be plotted. And we say on x-axis should be date, and on the y-axis it should be temperature. Color of the line will be red, width of the line will be 1, so default. Type will be 1, and alpha is also 1. Alpha means transparency of the line. Namely, it has values from 0 to 1. So if you set it to 0.5, it will have 50% of transparency. So, for example, oops. Here it is. So here is our ggplot, line plot for the temperature in Ljubljana from 1991 to 2020. And we don't see much here in this plot, so we decided to zoom in this plot. So we wanted to know what were the temperatures in Ljubljana from 2014 on. What we did is that we added additional argument to the function and set that date should be larger than 2014, January 2014. And other arguments are the same as in previous line, but we changed the width of the line, also type of the line, and also transparency of the line. So it looks like this. So by changing the type, we got a more dashed type of line, and it's more transparent. If we go back to 1, we can see that it's more red. So in the next step, we will add horizontal and vertical lines to this existing plot. Namely, we want to find where the maximum temperature was, when did it happen, in the period 2014 to 2020. And we will do this by adding 2 additional layers, namely geom H line and geom U line, which stand for horizontal line and vertical line. But first, we will need to calculate the maximum temperature in this period, and then we want to find when this maximum temperature happened. And this is stored in these 2 variables. And now we will use the same line as before, but we will add 2 additional layers, namely geom H line and geom U line. So this part is the same as before. And here comes the new part. I'm sorry for long lines. now when I zoomed in the code, I see that I will have to move left and right to show you everything on the screen. So by adding, for adding a horizontal line, we said that we want that it is maximum temperature that we calculated. We say that width of this line should be 0.8 and the type of 2. And then a vertical line is the month when the maximum temperature in the period happened, and the same type of as it was set also for the horizontal line. So if we run this, we can see that we have added vertical and horizontal line to the plot. We can do this also in the basic plot by using plot function by using abline function. And as I said, the lines are quite long, so I stored, let's say, settings of a plot into a new variable, so we don't need to repeat all the line over and over again. So we just call in the next line name of the variable. So we store it to the variable p, and then in the next step, we will just call this variable p where all the settings of the plot are stored. And we want to add another layer by which we want to define what will be the title of our graph. And we do it by the layer GG title, where in the brackets we can either write what our desired title is, or by using function paste, which was also introduced by Lawrence before, meaning that we can write part of the title, and then we, let's say, call some value from the data we are using. And we also define a separator here, which is actually default, so it is space. So first example looks like this. So we defined by writing what our title should be, and in the next step we are actually calling the name of the station, so we call Ljubljana from the dataset. And these are the basics of the line plots, let's say. And now we are going to the point plot. Here we will plot the temperature in Ljubljana. What was the temperature in Ljubljana? And I will run this plot, and I will explain what we did in the code. So I said that I want to plot data from the Ljubljana, and then by adding a layer geom point, we said that our plot will be scatter plot. And by adding aesthetics, we said that x-axis should be date and y-axis should be temperature. And then additional argument color, which is temperature in our case, says that we have a gradient color, meaning that lower temperatures are darker than the higher temperatures. And we also can define, similarly as in the basic plot, the type of plot and size and so on. So also here is a link to the website when you can find all the available shapes for the ggplots. However, as I said, point plots, the shapes of the points in the point plots are numbered, are defined by the numbers, but for the types of plots of points larger than 20 have also possibility to define outside and inside color. So not just one color, but also the outside and inside color separately. So we will again call the data from CL dataset, so the datasets where the two tables are joined. We will say that the plot will be point. Here are defined our data. Then our fill color will be according to the temperature, and the outside color will be according to the station. And then our type is 21, and the points will be a bit larger. And here we also define some other colors, gradient colors. Let's look. So as I said, outside colors of the point define the station, while inside color, namely the red ones, the gradient of the red color defines the value of the temperature. We can also modify the axis. We can also set it to the continuous if our data enable us that. And we can also change the limits of our plots and so on. We will look this on the example. And again, due to the long line, we stored settings of a previous plot into a new variable, namely P1. And then we are just adding new layers. All these layers are predefined. You can also create your own, but I think a lot of options are already covered by predefined layers. So we will define our axis, y-axis, as continuous, meaning that all the values on the y-axis can be so the temperature can have any of values between some limits, and we said that the temperature should be plotted between minus 10 and 30 degrees Celsius. And we also said that our x-axis will be of type year-month. This is also predefined. And our limits will be from 2009, from December 2009 to December 2020. And this graph looks like this. As I said, Ratec station is located more in mountainous areas, so lower temperatures are obtained at this station than in Ljubljana station. We will add also labels to some to the points on the plot. We will do so by using geom text layer, which is added here. So we shortened the period so the labels are visible on the plot then, and we can define what will be the size of the labels, how far from the point should the labels be, and what should be plotted against each dot. So we do it by geom text layer. Alternatively, it can be also done by the layer geom label. Now we go to the histogram plot. I will first run the code and then I will explain what's plotted. So we used precipitation data from both stations. And it's actually a distribution of precipitation in the period 1991-2020. And columns of this histogram are colored according to the station. We have precipitation on the x-axis and count, so number of months with such precipitation in the period. We defined the bin width. We said, okay, our bin will be 20 millimeters wide. We could do it also alternatively, so we could say also how many bins do we want to have. We also defined the colors of these histograms and outside colors. So this is nice presentation actually of two stations on one plot. And now we will add a frequency polyline to this plot. which actually connects all the maximums of these bars on the graph. So green line corresponds to the Ratece station and Ljubljana and red one to Ljubljana. And in the next lines, some options for multi-panel plots are presented. I will just go through facet grid and facet wrap options. Other you can run alone, and then I will show you also how to save your created plots to computer. So first we will use facet grid function. So it means that on the same figure more than one plot will be shown. And again, I will store or save some settings of previously used graph into a new variable P2. And then I will just add some additional settings or layers to this P2 variable. As I said, I will use facet grid option or facet grid layer, which means that if I run it, that our plot is split according to each station. Here we can also change our scale of x-axis. We cannot change the scale of y-axis. And now it is fixed. It is set to fixed, which means that both stations have the same limits of precipitation on the x-axis. But when we set it to free, it means that it adjusts to the data of each station. Oops, I went the wrong line. So the Ljubljana station has limits from 0 to 500 and Ratece station from 0 to 600. I accidentally ran another plot before, so here it is plot by using facet wrap function. The difference between facet wrap and facet grid is that here in the facet wrap we can also adjust scale of the y-axis, not just x-axis, as we learned before. And we define how many rows or columns of graphs we want by just using this argument n columns or n rows. So we have one column. In one column, two plots are shown. So if we change this to rows, we will have two plots in one row. As I said, melting and faceting by variables and so on, you can go through the code later alone, because we have a lot to show you through this introduction part plan. And I will show you for the end how to save your created plots to your computer. You can use a code to save it. For ggplot, you can use ggsave function, or you can just go here to this panel and go to export and save as image, where you define the width and height of your plot. You can also define the image format and the location where you want to save and so on. And here is also a preview of your plot. The second option is to do it by using function ggsave. We want to save this plot, which is saved under the variable plt. And then we call this variable. So we want to save this variable plt, and we want it to be called ggplot ggsave.png. So this is the name that we will see in our directory. And here is the width of the image and height of the image in units centimeters. There are also other options of units you can save your images in, for example, DPIs or inches or so on. So you have to define which units to use. So I hope I was clear enough to introduce you some basic plots that can be made by using R, both by using a basic function plot or by using a package ggplot2. So I give my words to Andre.
Okay, thank you, Claudia. I would like to share my screen if you stop sharing your screen.
Yes.
Okay, thank you. So here we are going to more advanced topics, let's say. So first, we repeat something because I will work with the same data we have in the introductory session folder, but I have saved this data somewhere else, so I need to define folder. setwd function brings us to this folder. So I will again load the precipitation file as with the same way, using the same way as Lawrence did. Then I need to load the tidyverse package because I will work predominantly with the tidyverse package, and the packages, or this is the ecosystem of packages and the packages which are included in this ecosystem. I will work with them. So nothing was printed here in the console at the bottom because I already loaded this package or the ecosystem of packages. Now the stable function converts the data frame to a new format of tables within R, which is this format is called table, and we can see. I can print the table in the console simply by writing breadths here, and you can see that this format is somewhat different from the format data frame. Mainly, you can see also you can see the information what type or what class is each column here. And if we had some negative values here or 0 values, they will be printed in red color. So you can see much better the differences between the numbers. We have the date column here as a character string only, so we need to convert this character string to the date. We use here the mutate function, for instance, and the pipe operator. Is it fine, everything? Yeah?
Yeah, sorry, I just...
Okay, so now we are pivoting the wide format to long format. So I call this object breadth L. We can also see the difference between the wide format which we have above and long format which we have now here, pretzel. You can see that date is the first column, then we have the station. Originally we had the station as the names of the columns here in the wide format, and now we have the station column here, and also the precipitation value column here. Now we are loading the package lubridate, which works with dates and times, and lfstat, which was used by Claudia as well. This is package devoted to working with indices related to drought, dry spells, and low flows, let's say. Now we create new columns year and age year, because we want to have here calendar year and also the hydrological year or water year. We use here the format function here because the water year, which is the function from the lfstat package returns for the class called factor, and we don't want the factor here. We want to have here the numeric, maybe, or character if you want, but we wanted numeric column here. So now we have, sorry, so we have here 2 additional columns, hydrological year and calendar year. And now we aggregate or group this table by calendar year and hydrological year. We can use also see the aggregated or grouped variables here. Right. Yeah. And we want to see, for instance, how many missing values we have in the table. And now we are using the wide format spreads, and we are going from the second column to the column 332. We are working with columns, not rows. If we worked with columns, we would write 1 here instead of 2. And here we wrote a simple function, our own simple function, which gives our the sums of truths. Is and a is the function which returns true or false if the value is missing, or if we have the real value here. So the sum here gives us the sum of truths, and we see that there is no missing value in the wide format table. We will now want to see what hydrological years we have in the table. So we have the hydrological years from 1941 to 1951 here, and we would like to see how many monthly values were included in the table. So we can see that we have also some incomplete years here. So we will restrict our focus only to the years which are full, which are complete. And so we are doing this. We only selected the rows where the number of months was 12. And we now see that we have 1942 to 1950 hydrological years here. They were originally full. Please note that in the Czech Republic, we use hydrological year starting from November of previous year, calendar year. But you can also set the water year function with other months starting the hydrological year or water year, if you use the water year function from the package lfstat. Now we are loading the package readxl for loading or reading the XLS files or Excel files. We now loaded the coordinates from the files and other metadata of the stations. I apologize here because this data set is not representing the Danube countries region. It is representing the Ebro river catchment. Sorry for that, but we use that data from the package which is devoted to hydrology also here. But and this data set is included in the package, so we can use it without any restrictions. So now we are going to join the tables, the table with hydrological years and the data of precipitation and the coordinates and other metadata. So we now see that the tables are joined, and we wanted to join only based on the rows that are full. So because the table on the left-hand side does not include some of the stations, precipitation stations. So we only we want to have the rows full, so we used inner join here. But know that there are other types of joins, left joins and right joins, and also nested joins. So please read the help page of these functions. Length is giving us the number of sub-basin of the Ebro catchment. You can see that we can also combine the pipe operator with different functions. Pulls only the one vector from the table. There is a difference between tables and data frames in that they data frame can be or if you want to select only one column from data frame, you can use the dollar function and also the square brackets where you have the indexes. While for tables, and you will be given the vector. Yeah, this is the result of indexing. But in the case of table, you will be given another type of table, which includes only one column. This is the difference. So now we wanted to select some station column and also the basin ID. Then we have the warning here that some NAs or missing values are here. So we can restrict our focus only to the rows where the NA sign or NA character is not included. This is done by that. If we use the NA, I can show you the help page of read XLSX. There is also the argument related to coding the missing values here. And originally we had these quotes here, double quotes. But we also can define the characteristic NA that it indicates missing values. Now, currently we have the character string here, so we restricted our focus on the non-missing values here, or the rows including non-missing values, using the character that it is not equal to NA character with quotes here. But if we correctly coded the NA values here, we would use the NA function here, which returns the logical answer. Here we have some other chain of pipes, and this is to compute the long-term precipitation values. So we have now the long-term precipitation values. We also are joining here, and now we are only checking how many missing values we have here regarding elevation column. So we see that there is no missing value. We can continue with that table. So now we are approaching to creating or building the models, linear models, because we want to, for instance, see if there is a dependence of precipitation or long-term precipitation on the elevation. So we are using now here the function ln, which means linear models, which creates linear models. And the first argument of this function is so-called formula. Yeah, formula can be can have their own session here because we have a lot of operators we can use there. We can use plus signs, also multiplication sign, parentheses, and also powers. So there is no time for explaining everything. Please study the help page of this, for instance, as formula function, because we can also convert the character string to formula. If you would like to write some functions and to have the formulas within the function, it is a good way to first paste different parts of string and then convert them to the formulas. So we are creating now the linear model here. On the left-hand side, we have the dependent variable. Then there is a tilde, and there is an independent variable elevation. And data indicates the table or data frame table which we are using for creating the linear model. So we can see now that linmod is some list of information, and this information can be summarized by the function summary. And you can see also that there is more information, and we, for instance, see the R-square here, adjusted R-square, also the coefficient, regression coefficient, which is called here elevation, and the triple asterisk indicate that the models or the coefficients are significant at the level of 0.0001. So the model seems to be quite good. Sometimes we need to transform the data to the to have there the Gaussian or normal distribution. We can also check if the variable precipitation long term has the normal distribution or obeys normal distribution by using Shapiro-Wilk test, for instance, and we see that we don't have the Gaussian distribution here. Also, we can test if scaling of the variable, which means the if we this means that the variable has 0 mean and standard deviation of 1. Yeah, scaling simply to, because if we want to compare something to the standard normal distribution, which has of course 0 mean and 0 and 1 and standard deviation of 1. So we can see, for instance, here that the Shapiro-Wilk test is not dependent on scaling. the variable. We can also try some transformation of the variables here. For instance, logarithm. We can see that the statistic of the test change slightly, but still we don't have the normal distribution here after the transformation. Also, we can create a new model with transformed variables. You can see that according to the rank of the model, there is no difference. So we should maybe fiddle further in order to get the normal distribution for the precipitation log, because linear regression usually requires the dependent variable that obeys normal distribution or approximately normal distribution. Okay, we can also see the summary statistics for the second model, and we can continue with other tests that gives us the information if there is the dependence between the variables. We can also use the correlation coefficients. There is a function core test. We can use the Pearson correlation coefficient, the Spearman correlation coefficient, and Kendall coefficient, which are built in this test, in this function. So we can see that there is the correlation Pearson. There is Spearman's law, which is based on ranks, and Kendall also non-parametric correlation coefficient, which is lower. Continuity, the parametric continuity means only that we are approximating the discrete distribution by the continuous distribution. So there is a continuity correction. Yeah, linear model here is linear model 3, summary. And the third linear model, please note that we have more than one independent variables there. We have also added the coordinates from the table here. This is the additive model, because we have the plus sign here, but also we can have some multiplicative models with this sign, but usually they are used for in different cases. Here we as well have the linear model 4 with transformed variable p long. HW here is again, we are going to the white format of the table here. And this was only to create a correlation matrix, because we can use also core function, and the core function can be fed by the matrix or table. So we are creating now the correlation matrix, which gives us all the combinations of correlations. And this is really correlation matrix, which has the diagonal that consists of unities here. And now we can also compute the variances of these variables. And for instance, if we would like to have the variance covariance matrix computed from the correlation matrix and the variances here, we can do it by premultiplication and post-multiplication of the correlation matrix by the square roots of variance matrix. This is matrix that has only the diagonal, non-zero diagonal, and the diagonal includes the variances of the variables. So if we have covariance here, can also compute the square sorry, I maybe didn't compute something. Yeah, this is the covariance matrix now. Also, we can also use the function SD, which gives us the standard deviation. Yeah, covariance 2. We can also use cov2 core function, which converts the covariance function to correlation function. And we can check if the correlation function are the same. Correlation matrices are the same, and it gives us true. We also sometimes need square root of the summed elements of the covariance matrix. So we can do it like that. And sometimes we need to, in short, I will give you the information about using these functions related to distributions, which are Q norm. This is a one-tail function of the standard normal variation distribution. This is a very typical value which we use in hypothesis testing, minus 1.96 approximately, and the opposite one. And we also can use other arguments of this function Q norm, but we also have not only Q norm, but there is also T norm, which works with the density function. P norm is the cumulative distribution function, and so on and so on. And R norm is the function which creates the random numbers from the Gaussian distribution or normal distribution. We can write also to some Excel files, and we usually now use write Excel package, which includes the write XLSX function. Now we have some table written to this to the file Excel file, so we can check if the file is there. Notes, our workshop, and the first is here, first folder, and the file is here, and you can distribute it to your friends, for instance. I think we don't have any other time here, any more time, so we have to end here. We answered some questions in chat, and also if you would like to ask something, you can ask also via email or so on.